So I have mentioned the lever rule in other lectures. Anytime we have this two-phase region, and I just like to do the lever rule on the one that you're probably going to experience the most, and that would be when you have two phases or two liquid layers. So you mix two solvents together, you think you're going to, I don't know, maybe you make a mistake or something like that. But anyway, you end up with two layers. You can measure their relative volumes pretty easily by putting them in a graduated cylinder. And you have the total volume, and you got the volume of layer 1 and the volume of layer 2. Now, just practically thinking, what layer is going to be on the bottom and what layer is going to be on the top? It's by density. So the more dense layer will be on the bottom, the less dense layer will be on the top. A lot of times, our common experience is be an aqueous layer and an organic layer. Okay. Now, you can't always say that the like oil floats on water, right? So you can't always say though that the organic layer is on top, because it might be chloroform or something that's really dense and has a lot of halogens. And so like if you have a chloroform layer, that's going to be on bottom and water will be on top. If you have any of these fluorinated solvents, they're very dense, and so they'll be on bottom. And so you could actually make a three-phase solution. You could have a halogenated organic layer, then you could have an aqueous layer, then you could have a hydrocarbon layer on top. And you could get different dyes and things, and you can make, every once in a while we don't really do much in the summer, but one of the demos we would do would be a red, white, and blue graduated cylinder, okay? And that one's pretty easy to make. You have, it's a nasty mess though. Brake fluid, we didn't use dyes. We just put brake fluid in the bottom, and let's see, was that on bottom? No, I think it was Dawn dishwashing detergent was on bottom, because it's really dense, and you just gently pour milk on top of that. And so that was the blue, and then the white, and then on top you had brake fluid, which is red. But that's a nasty mix. Dawn dishwashing liquid, milk, and brake fluid, and the milk eventually sours. I know all of this because I left it in the lab for like weeks. I went in there and I was like, what is that? So I had to put that in the waste. Anyway. But it was, you can make three layers, you can make multiple layers. It's just based on density and miscibility. So miscibility, if something's miscible, then they mix in all compositions, right? There's no phase separation. I put this in just for talking about immiscible liquids. You can distill immiscible liquids. It's just kind of hard to think about, though. You've got two layers there. You're putting heat into it, and you have a vapor phase composition above that. And it's sort of difficult to kind of conceptualize in my mind how you're boiling sort of this immiscible mixture when the heat source is at the bottom. So the heat's going into the bottom layer, but it's equilibrating with the upper layer, and then there's a vapor phase composition. So there's a lot going on when you're boiling immiscible liquids. But we use this in industry a lot, and that is steam distillation. So steam, the water and the oils don't mix, but yet you can distill these oils over with steam. And so essentially when something is at 1 atmosphere pressure, it's boiling, and it can volatilize, and it can get it up into the gas phase, and you can get it into the condenser and into the collection flask. Now, why would we do that? Well, if you want to extract peppermint oil from peppermint leaves, you can't just boil it out, because the oil will decompose before it boils. So a lot of these heavy oils, like essential oils, that's really popular now. They are extracted from their source using steam distillation. And in Oregon, there's just so many days of sun and rain that it was a great growing place. So a lot of the fields, here we have cattle and we have hay fields and fences everywhere. In Oregon, a lot of their fields were just grass seed, like rice seed for planting grass, mint fields. And so there was no grazing. Some places had cattle, but a lot of times it was just field after field with no fences, because there were no animals really to contain. And so it was just absolutely gorgeous. And there was a field near my house that was a peppermint field. And they would come through and harvest the peppermint, and they would go steam distill it and remove the oil. And they would come back with all of this like crushed, decomposed, steamed vegetation that was really broken down, and dump it in that field. Well, there was still a lot of peppermint oil in it, like you could smell it. So when you drove by, it was like peppermint. It was beautiful. And then this sort of broken down cellulosic material was great mulch and compost. So then they just offered that for kind of like a goodwill offering. People would come and they would take some and they would leave money in the box, and it was really pretty cool. So they would use steam distillation to get those essential oils out of those different plants. Let's talk about mixing. What makes something miscible or immiscible? This is a little bit about next week's lab, the Hansen solubility parameters. So we have this delta G of mixing over here. This is sort of the equation that governs everything. And it's got two parts. It's got an enthalpy of mixing and then this entropy piece. So the entropy of mixing times the temperature, and that's subtracted from the enthalpy. And so in many cases, the enthalpy of mixing is positive, right? Molecules like themselves more than they like the mixture. And so it's uphill thermodynamically. It takes more energy to pull apart the molecules from each other. And then when you put them back together, you don't get that energy back. Okay. The worst case scenario would be close to 50-50, where you've pulled, one part of the liquid A's molecules apart and one part of liquid B's molecules apart, and then mixed them together. And that's the most disruptive situation. And so we have this sort of maximum near the 50-50 region. But if it's asymmetric, then sometimes we can get this Gibbs energy that goes positive. Notice that the entropy of mixing is always symmetric, and it's always a minimum at 50-50. So this is a little asymmetric. The 50-50 point, or the highest enthalpy, is a little too far to the right. It's above 50-50, and it sets up this region. So the green curve is the delta G of mixing. And you see in this region, the delta G of mixing is negative. So it spontaneously mixes in those regions of concentration of A and B, or in this case, nitrobenzene and hexane. And up in this region, the delta G is negative. So if we have mostly nitrobenzene and a little bit of hexane, that's not a problem. It'll mix. But in this region, that's positive delta G. So we have two layers. Does everybody understand how delta G governs, whether you have two layers or not? If you have a negative delta G of mixing, you have a single layer. If you have a positive delta G of mixing, you've got two layers. And the equilibrium points are going to be right here where delta G is 0. So that's going to be the composition of layer 1, and this is going to be the composition of layer 2. Where that delta G is 0 are the equilibrium points. Getting that in your head? Okay. And so if we come down and draw those points as a function of temperature, and all of this is a function of temperature because of the entropy term, then we have this phase diagram down here. Notice now we have a temperature axis. So we change the temperature, we change the entropic component of that. Maybe we could raise the temperature enough where the negative piece would overwhelm the enthalpy. You see over here, the minus T delta S. So we could raise that temperature enough so that the entropy term takes over and it's miscible at all concentrations. And that's this region here. This region here is fully miscible. So this is one layer. Why is it one layer above that temperature? It's because the temperature is high enough that the entropy term makes everything spontaneous. Down here, in between these things, is two layers. So this is a partial miscibility phase diagram. Now, what we have not shown on here are any boiling things. This is just the liquid phase. So this is the composition of the two liquid layers. Okay. Now, in my research with cleaning and making solvent blends, this is very important because I might determine that to remove this buffing compound from an optic of glass, I I need a certain solvent that will pull that off. And I can't find that solvent, or all the good solvents are banned by the EPA or something like that, which is totally legit. Okay. So then I've got to go make a blend. And that's what your lab is next week. You're going to take a plastic surface, you're going to put drops of different solvents, 20 different solvents on there, and you're going to see which solvents attack the surface. We're going to call those good solvents for like dissolving that substance. And then you're going to put like a sphere around all the good solvents and exclude all the bad solvents from that sphere. So you've got a region in Hansen solubility parameter space that will tell you if you've got a good solvent or a bad solvent. And then you're going to make a blend of two bad solvents that will interact with the surface. So these might be two bad solvents that I can buy that aren't banned, and this is telling me how to blend them to get them to behave like a good solvent that I can't use. So this is the solvent formulation puzzle that we solve. So here's the math behind that. So this is the delta G of mixing for an ideal solution when delta H is 0. It's just the entropy term. Okay. And then these are the delta V of mixing, so the changes in volumes of mixing, so there's 0 if ideal. And here's the delta H of mixing. Again, 0 if it's an ideal mixture. And then if it's not an ideal mixture, we have this difference term in terms of the Hansen solubility parameters. Okay. And here's the total volumes, and all of these things go in. I'm not going to really walk you through all of this, but I'm just going to put the math in here for you. And delta G is 0 at these critical solution temperatures. And so here's that upper critical solution temperature. Now, what does it depend upon mostly? Differences in our solubility parameters and differences in our molar volumes. So we have densities, and HSPs, which we'll learn about. So if we have a big difference in the Hansen solubility parameters or a big difference in density, we're probably going to have a partially miscible solvent blend, and we'll get 2 layers below a certain temperature. This is the equation that will tell you what that maximum temperature is. Let's get to the lever rule before we run out of time. So these partially miscible liquids have this upper critical solution temperature, although that term is the one that I remember in my head mostly and the one I'll typically say the most. Now they're trying to change it from critical solution temperature to this consolate temperature, upper consolate temperature, like a consolidation or consolate temperature. So why they do that? Because they don't want to confuse you about the critical temperature, critical pressure, and critical volume of a gas or fluid. And so if you just, by context, you shouldn't be confused though. We're talking about 2-layer liquids. Okay, so that's this TUC is right here, right there. Well, you can see it listed over here on the temperature axis. So above that, you have 1 layer. Below that, you have 2 layers. And that's what you see on the graph. Above that, you have P equals 1 phase. Below that, you have P equals 2 phases. Now, over here on the left, you still have P equals 1, right? You can have a slightly dirty solution there. Or over here, you have a slightly dirty solution. But if you add enough of the non-miscible component, then you get 2 layers. So you can have a little bit of water in oil, and it won't separate. But you put enough water in oil, then it'll separate. And these lines here show you that the layers are not pure. That's the thing that I didn't understand until I took PChem. Is I thought if I had 2 layers of liquid, that they were both pure. Like if I mix A and B and they make 2 layers, I figured the A layer was pure A and the B layer was pure B, but no, not necessarily. You see how far away this curved line is from this wall over here. This wall is pure B. This is pretty dirty B right here. And this wall over here is pure A. And this is, very dirty A. There's a lot of B in A here. And there's a lot of A in this layer of B. So after today, you should be able to calculate the concentrations of those layers. So here's an example of nitrobenzene and hexane. At temperatures, we've got overall composition, and so here's where Z really comes into play. So overall, we have a composition of 0.41. So that's Z for nitrobenzene is 0.41. And so we're on this line right here, and we have another iso. So what are the isos that we've learned so far? Isobar, which means what? It's constant pressure, yeah. What is the constant volume one called? It's a weird one, isocor, C-H-O-R, isocor, okay? And then temperature one is called isotherm because it's temperature. This is a constant composition. So what would you call that one? Okay, isopleth, yeah. Oh, it does, very good. Isopleth, I just didn't point it out. So we're on that 0.41 isopleth. That's for the whole container. Okay, you got that? That's for the whole container. And so at this point here, if we're at 290 temperature, we've got two layers. This is one layer here. This is the other layer there. Okay. And so at 290, this XN, that's the mole ratio of nitrobenzene, is 0.35 in the A prime layer and 0.83 in the A double prime layer. Okay. So do you see that? So that's the composition of those 2 points. So this is what it would look like. The A prime layer is closer to our isopleth of 0.41. And so what does that tell us? That tells us that there's more of that layer. So A prime is big. Okay. So think of the seesaw. We got a really big kid on this end and a little tiny kid on the other end for it to balance. Okay. And so there's more moles in the A layer. It's hexane rich. And then the A double prime layer is nitrobenzene rich. And nitrobenzene is going to be more dense because it has the nitro and the nitrogen and the oxygens. It's benzene, so you got all those carbons, and essentially you've removed the hydrogens. So it's a smaller, it can stack and pack better. So the nitrobenzene is going to be more dense than the hexane. So it's going to be on bottom. So we know their relative compositions by mole fraction, but we don't know how many moles are in each of the layers. Like where is all of our analyte or whatever that we're looking for. And so here's the lever rule. So reading that graph, Z 40.41 is the total mole fraction of N across every phase. And it's across the entire mixture. A prime represents the association of with the hexane rich layer, and double prime is the nitrobenzene rich layer. And those values, those lengths, are called tie lines. Okay. Because they tie the middle to the outside edge. So we tie those straight across, and that's the distribution of the total moles across. So these are the governing equations for the lever rule. So when we talk about the lever rule, this is the equation we're mentioning. We leave unstated, though, that there's conservation of mass, right? If you've got the total number of moles, they have to add up. So we can use that lever rule to figure out how many moles of nitrobenzene are in each layer, how many moles of hexane are in each layer. And we can check our work by adding them all up and seeing that it's 0.41. Okay. So this is the lever rule calculation. Let's just assume that we have 1 mole total. It might be given that there's a different amount. Maybe it's 10 moles. Maybe it's 4.6 moles total that you put into the mixture. But in this case, we'll just start with 1 mole. And using that lever rule, we can rearrange it slightly. We can easily calculate the lengths. The things we don't know are the number of moles. So we'll put the number of moles on the left, the lengths on the right, and we can calculate those lengths. So this length here is 0.83 minus 0.41. So that's this first one here. You see where the numbers come from. I've got a 0.83 there, and I've got a 0.41. So I'm calculating the length of A double prime. The same for the bottom, the denominator. I've got the 0.41 in the middle, and I've got the 0.35 on the left. When I do the differences and divide, I get a number of 7. So I have 7 times more moles in the A prime layer than I do in the A double prime layer. So substitution then shows that, since A prime here is equal to 7 times A double prime, I can put this piece in for that. And I have 7 times the number of moles in A double prime plus the moles in A double prime equals 1. So I have 1/8. So A double prime, the number of moles in that layer is 1/8 of a mole total. And so then I should have 7/8 of a mole in the A prime layer. Okay, 0.875. So now I know that there's over here, let me find my pen. I have 7/8 mole and 1/8 mole. So that kind of gives you the relative amounts in each of those. If I know the molar volume of those mixtures, then I can calculate the actual volumes of those. Now, when things mix, the volume changes a little bit, but it'll give you a really good estimate. So it might change a few percent. So like you predict that it would be 60-40, and it might be 58-41 or something like that. It might not even add up to 100, but it'll be close. Okay. Now we find the number of moles of each component. We just use those mole fractions. So I know the number of moles total here. This is what I calculated from the lever rule. And so then I just take the nitrobenzene component, the 0.35, times that A prime concentration, and I get the 0.31 moles of nitrobenzene. 1 minus that would give me the number of moles of hexane. So 0.65 times this would be the number of moles of hexane. Okay, and I can do the same for the A double prime layer. I can take the mole fraction for that layer here times the concentration or the number of moles from the lever rule, and I get 0.1 moles of nitrobenzene, and 1 minus 0.83 is 0.17 times the total number of moles in that layer, and I get 0.02 moles of hexane. And then they all better add up to 1. So I could check my work, and 0.31 plus 0.57 and all that equals 1 mole. And then the nitrobenzene ought to be 0.41. So 0.31 up here plus 0.1 gives us 0.41 nitrobenzene. So you can check your work in both ways. So that's the lever rule problem applied to a partially miscible system. Again, if I know the densities of those and the molar volumes of those substances, then I can predict the volumes of each layer. Okay, and so that's all we've got for today. So the lever rule is not anything to be afraid of.